Extrema of functions of two variables. We're just looking at very neat applications of the partial derivatives of the gradients. That's basically what we're doing. Um, in calculus 1, we talked about finding the so-called relative extrema, the relative maximum, the relative minimum, by using the first derivative test, the second derivative test. Here, if you have a function of several variables, here in particular of two variables, we can find its so-called extrema, its maximum or minimum relative, by using what's called the second partials test. And so that's what we use here. Let me show you that. You remember in calculus 1, we talked about the difference between an absolute extrema and a relative extrema. The major difference is on the space or the surface that you're investigating. If you have a closed space, that is that all of the interior points and the boundary points are included, then it's possible, highly possible, to find an absolute extrema, because you may not have a relative, there may not be a curve, but you can always look at the endpoints to see if they're will serve as a highest point or a lowest point. So you can have a straight line that slants, and you could find its absolute maximum at its endpoint, its absolute minimum at its lower point. But that same straight line would not have a relative extrema. The so-called relative extrema we find in cases when we have an open interval, not to include the endpoints, and there you're looking for curvature. Remember, the first derivative and the second derivative test deals with the sloping of a curve, and so if there is no slope, if there is no bend, so to say, then the so-called first or second derivative test may fail, but you may have an absolute. That is, if you can include the endpoints, look at the highest point and see if that's a height or a maximum, if you will. So that's the difference between absolute and relative. Here we're concerned with, in this section, pretty much so the relative extrema, as it was in calculus 1. The extreme value theorem, really a copy of the extreme value theorem from calculus 1, but just here applied to the space of x, y, and z. Let f be a continuous function of two variables, x and y, defined on a closed bounded region or in the xy plane. The key here, the reason why you have an extrema, is that, again, the space or the region is closed. That's the key. Then there exists at least one point in R at which f takes on or achieves a minimum value, and there is one point where the function f in the region achieves a maximum value. The definition of the extrema, the relative extrema, is a copy of the definition for the relative extrema from calculus 1. That is, that if a point or if a point in the function is said to be here a relative minimum, that means that for all values of x, y in the function, those functions f of x, y will always be greater than or equal to this so-called minimum. And if there is a maximum, a relative maximum at x naught, y naught, then for all values, arbitrary values within that function f, all those values evaluated here for f will always be either less than or equal to this so-called relative maximum. But obviously here in x, y, z, we talk about some open disk. Right? In other words, that from x, y to x naught, y naught, we should be able to use the distance formula to be able to calculate the so-called delta disk. If there are any math majors here, make sure that whenever you go to a four-year institution to topology. Topology is the key to all of the high-level mathematics for analysis. Topology. It's an old course, but if that university offers topology, if you're going to study mathematics in a very serious way, take topology. Because in topology, you know, in advanced calculus, calculus on, when I took calculus on manifolds in graduate school, everything that they talked about was trying to prove all of these notions, but everything was based on some open disk or some ball, some epsilon ball, and you have to prove by showing how many balls exist that could cover a particular space, and that was all topology. So if you're not a math major, don't even worry about it. But that course I found to be the missing glue to everything of how math worked on a higher dimension. Definition of critical point, very similar to the definition of the critical point back in Calculus 1. That is, you remember in Calculus 1, we took the derivative and set it equal to 0, and then we found those values for x. We call those values so-called critical point. Well, here we take the partial derivatives and set those guys equal to 0. Take the partial of f with respect to x, set it equal to 0. The partial of f with respect to y, set it equal to 0, and then solve for those values of x naught, y naught, and we say that you have a critical point there. You have a critical point that can happen in either two ways. One, that the partial derivatives, when you set equal to 0, you can solve for x, y, you can solve for x naught, y naught, or that the partial derivatives do not exist. And so we say that there, very similar to Calculus 1, that there exists the critical values on those two criteria. A very classic, very important theorem, the relative extrema occur only at critical points if f has a relative extremum at some fixed point x naught, y naught on an open region R, then that fixed point is said to be the critical point. So and the statement is kind of backwards, because when we're building this in mathematics, you kind of want to find the critical point, then from there use some type of steps to be able to show that there's a relative extrema at that point. But here, if you know that at a particular point you have a relative extrema, well, that value must be a critical point. Duh, right? Here's the second partials test. This is what we'll use. So we hope that f is continuous, has continuous second partial derivatives on some open region containing some point a comma b. We call it a comma b because we hope that here a comma b is a critical value. So it's a critical point. We set the partial derivatives to equal to 0, and then you solve for some a and some b. Little d is the 2-by-2 determinant. That's all it is. Here, when you find that determinant, it consists of those second partial derivatives. And I'll show you the diagram of it in just a moment. If d is positive, hopefully you want d to be positive in order to get an extrema, a minimum or a maximum. So if the determinant is positive, and if it doesn't matter if you use the second partial with respect to x or the second partial with respect to y, you're supposed to be able to get the same value. But here, if the second partial with respect to x is positive, that is that the second derivatives, you recall from Calculus 1, denote curvature. So if the second derivative is positive, that means the curvature is upward. If it's upward, that means that I have a minimum, relative minimum somewhere. Right? here, for number 2, the discriminant is positive. If the second partial is negative, the curvature is downward. That means that I have a maximum somewhere, a relative maximum. So in a nutshell, what is this? This is the refining of the second derivative test from Calculus 1, but just now using the partial derivatives. Okay. If D is negative, I love this one. If D is negative, then this point is a saddle point, right? Now, where do we get the saddle point? Going back to section 11.7, what was that quadric surface that gave us remember we draw out that it looks elliptic paraboloid, exactly. That's when you run across guys like that. Right? Now, what does that saddle mean? That saddle is confusing, because when you look at that saddle, you have a minimum and a maximum together. Yeah, it's not coming out so good, but okay. So here's this discriminant again, discriminant, algebra. So this determinant, the 2x2 determinant, right? So that's what it consists of. It's the determinant of here. The first value is the second partial of f with respect to x, and then the mixed partial, and then down here in row 2, column 1, the mixed partial, and then row 2, column 2, the second partial of f with respect to y. Now, here's when we get the saddle. Look at this guy right here. Remember, this is z equal to y squared minus x squared, elliptic paraboloid. So look, see at the origin, you see that minimum, but then you also have a maximum. So the system is confused. Right? Yes, sir. The critical point is not found by D. You can have a critical point, right? You're saying an extrema.
Yeah.
So say that again now.
So if D is less than 0, with respect to x is greater than 0, then does that mean we just don't have an extrema?
Right. We have a saddle. Yeah. So if the determinant is negative, it doesn't matter about the values of the second partial derivatives. You will always not have a extrema. You have some kind of saddle point there.
What about if D is positive as a partial with respect to x? No, okay, that means we just have a.
Yeah. Yes, sir. Yeah. Let's look at a problem now. Find all relative extrema and saddle points of the function if possible. It might not have a saddle point. It may not have an extrema. Use the second partials test where applicable. So, we need those first partial derivatives in order to find the critical point. So this is 2x plus 8. Then the partial of f with respect to y is 2y minus 12. So we're going to set this partial equal to 0. These partials equal to 0. We get 2x plus 8 is equal to 0. That implies that x is equal to -4. And then the partial of f with respect to y is set to equal to 0. That implies that we have 2y minus 12 is equal to 0. Here we get y is equal to 6. So here we have a critical point at -4, 6. Now we find the second partials in order to use the second partials test. So second partial of f with respect to x is 2. Second partial of f with respect to x, then y I look at this first partial with respect to x, and then I take the partial of it with respect to y. Well, that's 0. You remember the mixed partials are the same, so that's 0. And then the second partial of f with respect to y, here this guy is 2. When I look at that determinant, it's supposed to be fxx, fxy, fyx, fyy. So this is 2, 0, 0, 2. Do you remember the determinant for a 2 by 2 is just the crisscross? Right? We just multiply like the 2 times 2, then minus these terms here. Let's put that in another color. So that's just 2 times 2 minus 0 times 0, so we get 4. We just need the sign if it's positive or negative. So here we have d is positive, and the second partial with respect to x is positive too. I think it was a 2. Yeah, right there. So it's positive. So if it's positive, that means the curvature is up, so I have a relative minimum. It's negative 4, 6. I need the function value as well. So this is f of negative 4, 6 is equal to it was x squared, so this is negative 4 to be squared, plus y squared, that's 6 to be squared, plus 8 times x. I'm just plugging this back into the function. Negative 8 times the x value is negative 4, minus 12 times y times 6 minus 3. You work that out. $55. Think you got it? It got erased off. Thank you. Sure is negative. Hadn't been wrong since 1976. Thank you. Thank you, Mr. Newton. All righty. Now let me give you one to do. Let's see if you can do this one. Can I go on to the next page? Is it okay? All right. Try your hand at that one. Let's see if you can get that one. So is everybody good with that? Do I have to work it out, or we can move on?
You still have to give points, or you just stop
It it says set a point where. So you want to get that point, right? So what did you get? 1/2, -1/2, and 0?
Yes.
Right. So you say set a point at that particular point. Yep. Very good. All right. See if you can work this one. So what we're doing is going by the second partials test. Did everybody finish that one? Did everybody finish that one? Some still working? I mean, I can wait if you're still working. Did you get it, Ryan? Okay, good. Um, we're going by the second partials test. I just pasted it right here again. Um, remember for that previous problem, you had D was negative, then that means that you have a saddle point, right? It's at the point A comma B, then you evaluate AB within the function to get f of AB. Now you notice something with that problem compared to this problem here. For this problem, whenever you get a minimum or a maximum, the signs for fxx and the sign for fyy would be the same. They'll both be either positive or they'll both be either negative. You notice for the saddle point that the signs for those second partials fxx and fyy would be opposites. One will be negative, the other be positive. Yes, sir. Exactly. You got that saddle again. Like you look at the curvature for one is going upward, and the curvature for the other is going downward. So that's what that's trying to explain. Yep. Yes, sir. Yeah, I work this one, then I give you one more to do, and then you can work that one, and then we'll be done for today. Find the partial of f with respect to x, negative 6x plus 3. If you set this guy equal to 0, that implies that x is equal to 1/2. Positive, right? Because of that negative 6, you get negative 6x equal to negative 3, then you divide negative out by negative, you get positive. Find the partial of f with respect to y, negative 4y minus 4. We set this guy equal to 0. That implies that y is equal to negative 1. Okay. Now we find those second partials coming from that first partial of f with respect to x. The partial of the second partial of f with respect to x is negative 6. The mixed partial, you get 0. Partial of the second partial of y, f with respect to y, is negative 4. So then we find d. This is f sub x, f sub x, y, f sub y, x, f sub y, y. So that gives us the negative 6, 0, 0, negative 4, and we get positive 24, right? So it's positive, and f sub xx is negative. So if it's negative, yes, sir. No. The mixed partials won't always be 0. No, sir. Just for these problems right here, they're coming out to be. Yeah, that's a good question. So again, the d is positive, and then f sub xx is negative. So if it's negative, that means that the curvature is downward, and we have a relative maximum. At the point, what did you get? This is 1/2 comma negative 1. What did you get for f of 1/2 negative 1? 31? 31 over 4? very good. Okay. Everybody happy with that? So just one more, if you could do this one, and then we'll see what you have. Hmm. That's the graph that matches with the equation. Was that the question? Yes. Yep. And Joshua, since you asked, your mixed partials here won't be zero. Yeah. Yes. Yep. You end up with two equations involving x and y. Just you can use substitution or um, elimination. You get a saddle point. Yep. It's the saddle. I think D comes out to be like a -3. I got 1 minute till time to quit. I'm just going to put the answers up here and you can finish working it. We get a critical point at 1 comma -1, and D is 2, -1, -1, -1, -3, f xx, 2, f of xy, -1, f of yx, -1, f of yy, -1. And so since this guy is negative here, ended up with a saddle point at 1 comma -1 comma -1. All right. Everybody's good with that? Yes, sir. Kind of. You got -2. You got -5. -5. Okay, yeah. I didn't have it on my paper, and I just guessed that it was -1. Thank you. So this guy was -5. Oh, it's -2. Gotcha. -2. So that's -4. Yep, -5. Gotcha. Thank you. Yeah, we want to be right. I don't know how come I didn't. Where's my value for that? I don't know what happened on my paper. Yep, good deal. Okay, man. Take care, Joshua.